We've looked at the topic of y equals mx plus c, that is straight line graphs, and we've seen that you get these things of different gradients along the graphs, sometimes with positive gradients and they're going from bottom left to top right, and sometimes with negative gradients as well. And even horizontal lines, and a special case that doesn't fit into y equals mx plus c, where it's a vertical line, x equals something. Today we're going to look at a different type of graph, or different types of graphs, and these are nonlinear graphs when you don't get a straight line. And so our first one we're going to look at are called quadratics, and this is when you don't just have an x term or a 3, you have an x squared term in there as well. Actually, something like y equals x squared itself is a quadratic, so just as soon as it has an x squared, basically the x squared is the highest ordered term, then it becomes a quadratic graph. Okay, so we've got a table to fill out. Now this is just to help us plot the graph. So actually the graph will extend beyond x equals 5. It will also exist for points 2.2, 2.4, etc. We're just going to get some nice whole number points so that we can plot it on. So let's give that a go. Actually, if you're feeling confident, pause the video and try and fill in the table yourselves. I'm going to start with the 2. So what I'm doing here is I'm substituting 2 into y equals x squared minus 4x plus 3. So that's going to give me 2 squared minus 4 times 2 plus 3, which is going to be 4 minus 8 plus 3. I'm going to do the 4 plus 3 first to give me 7, then minus the 8. I'm going to get minus 1. With the 4, I'm going to do, let me do it down here, I'm going to do 4 squared minus 4 times 4. Well, that's great because actually 4 squared is 4 times 4, so they're just going to cancel out, and I'm going to be left with 3. And the last one, this is the trickiest one, you've got to put it in a bracket when you square the minus 1. Or you could write minus 1 times minus 1. That's okay as well, but just be really careful, especially if you were to put this into a calculator. Then you would do 4 times minus 1. There's lots of negatives going around. But I'm going to get 1 plus 4 plus 3, and I'm actually going to get 8. Now looking at this, we see that there's quite a lot of symmetry going on. We've got a 0 either side, we've got a 3 either side, we've got an 8 either side. There's only a minus 1 by itself. It doesn't have a pair. We'll talk a bit more about that in a second. Right, let's plot the graph. So we've got an axis here, a set of axes I should say, and I'm just going to plot when x is minus 1, y is 8. I'm going to put a point there. 0, 3, 1, 0, 2, minus 1, and then remember I then had the same results the other side, so I'm just going to put these in, and it's going to look like that. Now that is not my graph, that's just some points on the graph that I have chosen to calculate. The graph actually goes through all these points, but like I said, it exists for other values of x. Now the other thing to say is that it's not going to be a straight line. So what I actually have to do, I can't just connect it with a ruler, I have to do freehand, trying to make it go through each of the points. Here goes. Oh, that was a shocking start. Let's try it again. Okay, that one's better. It should have gone through here. It's quite hard to do it on a screen, so it should have come like down around like that. Okay, and that is our quadratic graph. And what we see, well, first of all, this actually has a special name. It's called a parabola. And what we see is that, yes, we've got the same one either side. And the reason we didn't have it twice is because it's like, it's symmetrical. And this minus 1, what it's going through here, is actually on this mirror line. So this is a line of symmetry. It's actually x equals 2. And all quadratics will have a line of symmetry. And then secondly, actually, let me just say, I've stopped it there, but remember the graph does carry on going up. it doesn't say where to draw it between, so yeah, I'm just going to extend it either side. Right, the other thing to note is this point down here is given a special name. It's where the graph comes around from going down to up. The graph is turning, it's called a turning point. Sometimes it's called a stationary point, but that's more for A-level, you see that word. You normally see the word turning point at GCSE. So there we go, we've got our graph. Our first nonlinear graph is looking pretty good. Okay, oh yeah. Right, so we did this without a calculator, but there is a function on your calculator that can deal with it very quickly. And I don't just mean substituting the numbers in. Of course, you could do this. You could do -1 squared. Note you need to have the squared around it. -4 times -1 plus 3. And we get that 8 from before. If you don't put the squared around it, then you're going to get -1. That is -1, whereas actually we should be getting +1. So be really careful. Whenever you're squaring a negative, you have to put a bracket around it. Of course, when you're squaring a positive, you could put a bracket around it, but it doesn't matter. You're going to get the same thing. So we don't bother when it's positive, but we have to when it's negative. Hope that makes sense. Okay, but on to the thing I'm trying to show you. Right, if you go to your calculator, and you're going to have, a calculator similar to mine, but yours might have it somewhere else on the calculator. Okay, if you go to menu, then we've got calculate. That's what we've just been in. Then we've got statistics. We're not going to use that right now. We've got table, and we've got actually a ratio calculator, but we're going to look at table. And then you get f of x. Now that is actually a y. That is your function that you're interested in. So don't be put off by the fact it says f bracket x bracket. That is what you put in for y. And what we do is we go alpha x squared minus 4 alpha x plus 3, and we put our function into our calculator. Yours might be like mine, it might give you a second function. You could plot another one at this point if you wanted to. I'm going to leave it blank just so I don't cause confusion, so I'm going to just press equals, and then this start is my starting value for x. My first value is actually -1. My end value is 5, so I don't need to change that. And then this one is what I'm going up in. So I want to go up in ones every time. I'm adding 1 each time, and I press equals, and it gives me this table of values. So I can check it. I've done it without, done it correctly, or I could have just done it straight away with this. I press down to get the later values. Okay, that is our first graph done. Here's just a little summary of the steps I just did. Okay, it's looking good. We're going to do some more practice of quadratic graphs in a second. Here is a second question on quadratic graphs. Again, there's an x squared in there. That makes it a quadratic graph. This time it's got a minus in it. So let's see how that affects things. What I'd like to do is you can use your calculator straight away if you like, using the table function. See if you can fill in this table and plot the graph, and then think about what is going on. Okay, I'm going to go through this. I'm going to go straight to the table function. This time it's just 4 minus x squared. I'm starting at -3 and I'm ending at 3. I'm going up in ones, and I get my values -5, 0, 3, 4, and so on. So you can fill those in. Here's one I did earlier, and you can plot the graph. Here is one I did earlier as well. Again, we get a turning point. We get a line of symmetry. In this case, it's actually the y-axis, or x equals 0. And actually, I just realized one thing I've not talked about, I didn't talk about in the first one. I get these things here are where it crosses the x-axis, and we call these roots. So I'm not going to talk a lot about that today, but I'm just going to throw it in, and I'm going to add it back to my first one as well. They're also called the x-intercept, and this value here would be the y-intercept. I don't want to throw too many words out there, but there we go. Now this one differs, doesn't it? Because before it was going down and up, whereas here it's going up and then down. And this is a characteristic of all quadratics. If you have an x squared that's positive, you'll get this kind of quadratic. And you have a minus x squared, you'll get this kind of quadratic. And that's something that I expect you to remember. And to summarize, here we go. For y equals ax squared plus bx plus c, this is a general quadratic now. If a is greater than 0, we've just been looking at the case where it's 1. We'll get this kind of quadratic, and I call it a smiley quadratic. I'm not the only one who calls it a smiley quadratic, but you get this kind of curve. And then for a less than 0, like minus 1 or something, minus 2 or something like that, you get this sad quadratic. And the reason you get this is all to do with the x squared. When you have x squared, when x gets big, this is going to be big and positive. But when x gets big and negative, I'm doing like minus a million all squared, that will also give me a big positive number. That's why this behavior happens. That's why I get these things here. Somewhere in between, it's going to go down, and then it's going to have to come back up. And on the sad quadratic, it's the other way around. If I have a really big number, and I'm squaring it, I'll get a really big number. But if I then make it negative, it will be large and negative. And the same will happen for squaring a large negative number. That will give me a large positive number, but then making it negative will come out here. So actually, what happens is it increases and then it comes back down. Okay, so because what I'm trying to get across is it's actually quite, I want you to understand why it looks like that. Not just learn that it looks like that, but try and understand the reasons for the shape. And just to throw this out there, actually, when you look at suspension bridges, this little part here, the suspension bridge, what you get is a parabola. It follows, from engineering that is a very efficient kind of shape to use. And you'll get this line of symmetry coming down. It'll help with the stability of the bridge. This is the Clifton Suspension Bridge in Bristol at night. So that's one place where parabolas appear in the world. And even more naturally, when you throw a ball in the air, you'll know whether it comes back and up and down. But if you throw it off in the distance as well, then what you get, the shape you get, is one of these negative parabolas. It will again have a line of symmetry. It's got to be said, this is ignoring air resistance, which you might say I can't ignore, so you don't quite get this shape exactly. But it is very much like it, and if you did it in a vacuum or on the moon, then it would look very much like a parabola. There are some, it's not perfect, but it's really close. So that's interesting fun fact. We've now covered how to plot quadratics, 2 different types of quadratics. We've seen the shape, I've tried to explain the shape, I've talked about where they are in nature, and we've mastered our calculator function. It's all looking good. There's a happy parabola and there's a sad parabola. Today I've introduced nonlinear graphs and we've looked at quadratics so far, or that give you a parabola. It's got an x squared in it. Let's move on and look at some cubic graphs. So that is when you have an x cubed in there, and you might still have an x squared in there. Later on I do throw one in, but the fact that you've got an x cubed in there means that term starts dominating when you get large values of x, which is why we call it a cubic, and it will have a different shape. But the process of drawing the graph is exactly the same. Just don't expect the shape to be the same. Don't expect these happy and sad parabolas. You get a different shape. So again, I'd like you to use your calculator function and work through and get the different graphs and think about what's going on as you do so. Because this is like practice of plotting the graphs, but it's also getting you to think about the nature of the curves that come out. Okay, I'm actually not, okay, I'll do it. So I'll go back to table function. Hopefully you're happy with this by now. I go to alpha x, but this time instead of squaring it, I have to press this little, I could press the cube, or I could press this little button and put the 3. Either of those are fine. And then I have to press right, and then plus x minus 4. And again, I could, if I wanted to now, I could put in the second function. Why not? X, if I'm plotting multiple ones at once, it just might get a little bit more confusing if I'm reading off. Okay, but in both cases I'm starting at minus, whoops, that was not going to happen, minus 2. And I'm going up to 2, steps of 1. And here we go, look, I get my x values, I get my f of x values, and I get my second function g of x. And I can fill all these in really quickly. And what you'll get is this table here and this table here. Okay, you can see that it's that, and then you get this graph here and this graph here. Different type of shape, again, not joining up with a straight line, nice smooth curve. On the right hand one, you might have made it go down straight away, but you kind of got to follow along like the behavior of it, and so you expect it to kind of carry on going up for a bit and then down. That's why I've done that. You won't be judged too harshly on that, but that tends, we don't know for sure that that is going to be the minimum. You could even argue for some of the quadratics that I wouldn't know for sure, except for the symmetry. I suppose that's what gives it away. But anyway, these are the two I get, and they're slightly different characteristics going on. What are the characteristics? I want you to pause the video and have a think. What are the similarities and what are the differences? Well, I'd say the similarities that you kind of get this thing going from minus infinity going up to positive infinity as x increases. That happens in both cases. The difference though in this one is actually it goes up and then it comes back down and then it goes back up. Whereas in this one, although it kind of levels off a little bit, it never kind of decreases. That's the difference. Quite interesting given that you basically got the same curve in both cases. The only difference is that here I've got the plus x and the minus 4, and here I've got the minus 2x and the plus 3. So what is it, I wonder, that causes these kind of curves? Okay, well, I'll leave that. We'll maybe come back to it. Two more to try. Okay, one with an x squared in it. This is still a cubic. And then one where I've chucked in a minus x cubed. So please have a go at getting the tables done for these and plotting the graphs as well. Okay, here are the answers. So you get these tables. I'm pretty sure I'm correct. Tried this earlier. And you get these graphs. Note again, we get this up and then down and then up again, this time with an x squared. And then here, you actually get it flipped round because the minus x cubed just causes a slightly different behavior. So how can we classify these, and why do some of them go up and down, and why do some of them just go up or just go down? I want you to pause the video and have a think about that. Okay, I'm going to talk through this. The summary for cubics is as follows. If you have y equals ax cubed plus bx squared plus cx plus d, that is a general cubic. Remember, a, b, c, and d are constants. There might even be 0. You can't have a as 0 because then it wouldn't be a cubic anymore. But you could have b equal to 0, which we had in the first example, or c equal to 0, which I think I had in this third example. That's okay. And what we get is this. So we've seen that we've got some, for a greater than 0, we've seen this one on the right, and we've seen this one in the middle. I put this one on the left because that is kind of a special case where actually the gradient kind of becomes 0. It doesn't go back down, it becomes 0 for a bit. And actually it's worth writing down because this is what y equals x cubed by itself looks like. And then, although we only looked at one negative, okay, the same will happen. You can get ones that come down and then up, or you can get ones that look like a one example, or you can get this one where it comes down and it does level off and then go back down. This is an example of y equals minus x cubed. And what is happening is that basically there's a battle between all of the terms. X cubed is always trying to do this. But when you suddenly have an x squared term in there, it's looking like that. Or if you have a minus x squared, it's looking like that. And these kind of things are being added together. So sometimes one of them kind of might win out, and the same with positive x and minus x. So I just want to look at the example again. When I've got plus x, when x is getting bigger, when x cubed is getting bigger, x is also getting bigger, and that's why there's no battle here, because they're both getting larger as x increases. Whereas if I look at x cubed, that one's always getting larger as x increases, but minus 2x will actually have this kind of shape. So it's actually becoming smaller. And so you get this period, this region rather, here, where there's a battle between x cubed and minus 2x. I'm not even joking, they're like having a little fight, and minus x manages to win for a little bit because it's negative and an x cubed is becoming small. Minus 2x wins for a little bit, and when we start going down, but then x cubed kind of gets big enough again to take over. I'm not going to talk about any more about the properties. It's actually quite a complicated relationship going on. So, but all I want you to take away is that sometimes cubic graphs look like this, go up and down. Sometimes they look like this, and sometimes they look like this. So I often see this misconception that people think cubics will always look like that, where it's not the case. We need to be careful. But yeah, it's quite an interesting thing. I don't have any examples of x cubed graphs in nature. I'm sure there are some. They're probably just a bit more subtle, and you might want to investigate that. But quadratics are a bit more clearer, I would say. We've basically reached the end of the lesson. So today we've plotted nonlinear graphs. We've used the table function on a calculator to do it. We've thought about doing it without a calculator. We've plotted the points and we've looked at some of the properties. I didn't worry about labeling the cubic. You don't have a line of symmetry in the same way in general. Sometimes you get turning points, sometimes you don't. You do get roots. That is one thing to say, but that wasn't a focus. We looked at the battle between terms, and I tried to talk about that. Just to finish, this is more like an extension, if you're interested, you might want to investigate some Quartix. Can you write down some Quartic functions and then plot them and see if you could classify them? That's a little challenge. If you're up for it, go for it, and I'll go through it now. Otherwise, then hopefully you're at least happy with the quadratics and the cubics. Well done. Okay, I'm going to talk about the Quartix for you, awesome people that have stayed on. So here we go. Quartix, you get some different kinds. You get really interesting things going on. If you just plot y equals x to the 4 by itself, and maybe you didn't do one that was that simple, you actually get something that looks a bit like a happy or sad quadratic. The only thing I'd say is, and maybe I didn't accentuate it enough, is that it'll become flatter. So the quadratic might look like that, and the quartic kind of is more U-shaped. I probably should have accentuated that in my example. And for minus x to the 4, it flips around and you get this sad quartic. But if you start including other terms, then again you get all these interesting battles between terms coming on, terms happening, and this is what can happen. You can get this w or m kind of function where it goes up, it goes down and then up and then down and then up, or up and then down and up and then down. It always has to win out. You always know for positive x to the 4, it will always end up at positive infinity either side for the y value, and the opposite for minus x to the 4. But you can get these weird like squiggly things happening in between. It doesn't have to be symmetrical though. So sometimes, actually more commonly, you're more likely to get this kind of lopsided w or m, or the other way around. So I wonder if you managed to get that. If you did, or if you got some of them and you thought about it, then brilliant. Again, it is the battle between the terms. I won't say to do x to the 5, but you get also lots of interesting things going on there as well.